Hello friends. So, we have seen the finite elements of one dimension using C0 continuity, where only the variable of the governing differential equation that was required to be continuous across the inter element boundaries. So, that variable was the primary variable. So, this typically happens when the governing differential equation is of second order and the weak form, the highest derivative available in the weak form is only up to the first order. The second class, we also have another class of problems in one dimensional finite elements, where not only the variable of the governing differential equation, but also its first derivative also needs to be continuous across the element. So, these two, not only the variable, but its derivative as well, they are the primary variables of the problem, and therefore, the approximation has to be such that it has to be sufficiently smooth such that not only the basic variable of the problem differential equation, but also its first derivative is continuous across the element boundaries. So, the first degree continuity, first order derivative continuity is also required. So, the slope continuity. So, not just the function value, but the slope of the function, that also needs to be continuous. So, a higher degree of smoothness is required in the approximation, and that is covered under what we call as C1 continuity finite elements. So, what we are referring to is the beam problem, beam bending problem. Just to rejig the memory or the concepts, it is based on Euler-Bernoulli hypothesis, although it is a 3-dimensional deformation model. It is a 3-dimensional system, and deformation is of course all in 3 dimensions, but it may be possible that one length, I mean particularly in the case of beam, one length is one dimension is too large in comparison to other 2 dimensions. So, the cross sectional, so in the case of beam, the length is very large in comparison to the cross sectional dimensions of the members. So, a beam is typically a structural member whose length is large compared to its cross sectional dimensions, and it supports loads and or moments that produce deflection of the beam that in the transverse direction. So, this is the longitudinal axis of the beam. So, the deformation would be either in this direction or in this direction. So, these are 2 different planes of bending, as so to say. So, the cross sectional dimension are very small compared to the length of the beam, and the loads are in the transverse direction, either the loads are like this or the bending moments are applied. So, the deflections are transverse to the axis. Now, this has a very complete 3-dimensional state of deformation is of course too complex, and the problem becomes too, what to say, unwieldy if we try to go into continuum based modeling, and frequently a very good results can be achieved by imposing certain kinematical constraints on the deformation and developing simplified expressions, and those kinematical constraints are what we refer to as the Euler-Bernoulli hypothesis. Please mark the word hypothesis. It is an hypothesis because it is not a theory, and why it is not a theory I will come to that after in a while. So, the first hypothesis is plane sections normal to the neutral axis remain plane and normal during bending. So, the plane sections which are plane and normal to before bending, after bending and during bending, they remain plane and normal. So, it will be, and this happens when, and the Hooke's law is applicable. So, linear Hooke's law is applicable, and Young's modulus for tension and compression is same. So, it does not make a difference whether it is tensile strain or compressive strain, the modulus of elasticity, Young's modulus, is same for in both the direction, and Hooke's law is of course for linear elasticity. So, that obviously that itself implies that we are looking at small deformation domain. So, our frame of reference is small deformations, and beam is initially straight, right, like this, and its longitudinal fiber, they bend into concentric circles during bending, and the radii of curvatures which define this these circles, they are much larger compared to the cross section dimensions of the beam. So, now this is the kinematic constraint that is imposed on the deformation of the beam, and based on this very simplified expressions for the deformation, transverse behavior, transverse deflection, and it can be related to the bending moment and shear force or stress resultants in the beam, they can be related to that, and useful design quantities can be computed, the bending moment and shear force and what is the strain level, maximum strain and maximum stress that will develop in the beam, they can be calculated. So, why is that then an hypothesis? First thing is, as I said, the beam itself is a 3-dimensional body. Now, any 3-dimensional state of deformation will have Poisson's effect. If it stretches, if I stretch in one direction, all other 2 orthogonal directions, it has to undergo compression. Now, this Poisson's effect is neglected, is not captured by Euler-Bernoulli hypothesis, and therefore, the deformation field that is actually predicted by Euler-Bernoulli hypothesis is not really the exact deformation field that will be satisfying the governing differential equation in true elasticity problem. But still it is a very working good working approximation, in the sense that we get the values of the stress resultants, the bending moment and shear force, those are very good, very close to what would be there in a more rigorous analysis, and they can be computed with very little effort. So, very effortless computation. So, the Euler-Bernoulli hypothesis still provides a very good working approximation, and we continue with that. So, this is the like the equation. So, in this case it is a fixed cantilever beam subjected to uniform cantilever beam of length L and uniform flexural rigidity EI subjected to transverse uniform distributed load transverse to the beam axis, and the x is oriented along the beam longitudinal axis of the beam, and transverse deformation are along y direction. And this is the infinitesimal element free body diagram, and that will establish the equilibrium of forces, and using this equilibrium of forces we can derive the governing differential equations as the 4th order differential equation. I mean, the moment is this is the moment expression, moment is given by second derivative proportional to second derivative the curvature, and the second derivative of the moment, that is the rate of change of shear force, and that is related to the transverse force, transverse applied load. So, this is the governing differential equation. EI obviously greater than 0 is the flexural rigidity of the beam, and this differential equation is applicable over the domain 0 to L, that is the length of the beam. Now, this is the governing differential equation, and let us say if I approximate it using some approximation, let us say V hat, right. Let us say I need to find its approximate solution. So, let us I am looking for an approximate solution V hat as an approximation of V, and if I substitute the approximate solution in the governing differential equation, I will get the domain residual as d2 over dx squared multiplied by ei d2 V hat dx squared minus f, that would be the domain residual. So, we can substitute the approximation V hat in the governing differential equation, and we can get the domain residual as so that is the domain residual, right. So, if I develop the weak form, so weak form would be based on weighted residual statement would of course be the domain integral of this domain residual, that is equal to 0. Now, this is one dimensional problem. So, one dimensional problem, this is obviously equal to 0 to L W and R omega d omega, of course d omega. So, in this case omega is just x. So, this is equal to 0. So, after this I have this weighting function unknown as yet, but it is a function of x. So, I can use this this is a product of two functions, I can integrate it by parts in a sequence. So, I do it twice, and that is what leads me to this particular expression. So, this is the weak form of the weighted residual statement. W is the weighting function. So, this is the first boundary term W multiplied by dx of ei d2v by dx squared at x is equal to 0 to L, the two boundaries, minus another weighting function, another boundary term from the second application of the integration by parts, and then finally we have this symmetric function, symmetric operator term. So, second derivative of W multiplied by ei times second derivative of approximation V hat and minus W f dx. So, this is the original statement from the weighted residual statement, and this is equal to 0. So, there are two boundary terms here. So, now identifying the primary variables in this boundary terms. So, there are two boundary terms. So, obviously, there are going to be two primary variables and two secondary variables. So, the primary variable, first primary variable is the weighting function term. What is the form of the weighting function? 0th derivative in this particular boundary term. So, 0th derivative, and I replace the weighting function by the unknown of the problem. So, V, the transverse displacement. So, the first primary variable becomes transverse displacement V. Associated secondary variable is this expression. So, the third derivative of displacement, right. So, third derivative of displacement. So, this is obviously the shear force. So, that is the corresponding secondary variable of the problem. Now, looking at the second boundary term, the weighting function appears as the first derivative. So, the appropriate primary variable would be replacing W by the primary basic unknown of the problem. So, that is the transverse displacement. So, instead of so the primary variable becomes dV by dx. So, the unknown of the problem in the same form as the weighting function in the boundary term. So, first derivative, so dV by dx. So, that is the slope of the transverse displacement, and the corresponding term secondary variable, this is secondary variable and this is obviously the bending moment. So, the bending moment is the corresponding secondary variable. Now, you can have a look at it, the primary variable, secondary variable, they together appear, and it is always like a work quantity. So, this is the weighting function can be interpreted as the virtual displacement. So, this is like boundary shear force or the boundary force in moving through the virtual displacement at the boundary points, end points. So, the work done by the shear force at the end point in moving through the virtual displacement at the endpoints. Similarly, this term, the bending moment at the endpoint in moving through the slope at the endpoint. So, that is the work done. So, both of these boundary terms, they are always work quantities, and this is WF. If I am interpreting W as a virtual displacement, so this is again the virtual work done by the external force in moving through virtual displacements, and this is the internal energy, strain energy stored. So, this essentially weak form, particularly when we interpret it in the Galerkin approach, the W we use as the same thing as the approximation function, weighting function as same as the approximation function, then this becomes entirely identical to the statement of principle of virtual work that is so commonly so well known in the field of structural mechanics. So, coming back to the problem of finite element approximation. So, essentially there are two primary variables, the transverse displacement of the beam and its slope. So, first derivative of the transverse displacement. So, the approximation has to be chosen such that continuity up to first derivative is ensured across the nodes. Now, we have already discussed one such problem during our discussion of interpolation functions, interpolation theory, and that is Hermite interpolation. Hermite interpolation, they interpolate not just the function values, but also the derivatives of the function values, required order of derivatives. There are different orders of Hermite interpolation. So, in this case we require in continuity or interpolation not just about the value of the transverse displacement, but we also want continuity with respect to the slope of that displacement function at the nodes. So, there are these two values, these two terms and the two primary variables at the nodes. So, this is what the elementary finite element model looks like. So, element E defined by two nodes I and j, I left side node, j right hand side node, with 2 degrees of freedom at each node. So, primary variables. So, the transverse displacement V I at node I and the slope. So, theta I that is essentially the derivative of the transverse displacement V, and similarly at the node j the transverse displacement V j and the approximation the rotation theta j, and then there are associated secondary variables. So, these are the shear forces V I, V j and M I, M j, these are the bending moments at the respective nodes. So, a 2 node with 2 primary variables at each node to define the polynomial approximation. So, there are 4 constraints. So, the approximation has to satisfy the limiting conditions of these variables at these nodes. So, whatever approximation we choose, the displacement when it is evaluated at node I, the displacement should evaluate to V I, its derivative should evaluate to theta I. When the function approximation for V is evaluated at node j, it should evaluate to V j and its derivative should evaluate to theta j. So, these are the 4 conditions, 4 constraints that are required. So, with 4 constraints available, we can fit a polynomial for V. It is the polynomial approximation for transverse displacement V. So, with the 4 constraints available, we can have a 4 term approximation, and a 4 term approximation complete polynomial starting from the constant term would be a0, that is constant, plus a1x linear, plus a2x square quadratic, plus a3x cubic. So, there are 4 unknown coefficients of the problem in this approximation, and these 4 unknown coefficients can be evaluated uniquely by imposing these constraints of the approximation that has to satisfy at nodes I and node j. So, this is a cubic polynomial, and I can, this obviously has to be consistent with interpolation model. So, interpolation model is n 1, that is the interpolation function, first interpolation function associated with node I, transverse displacement at node I. So, n 1 v 1 plus n 2 theta 1 or theta I plus n 3 v j. So, transverse displacement at node j plus n 4 theta j, the slope at node j. So, these are the 4 term interpolation model for the transverse displacement, and similarly I can take the derivative, and this polynomial approximation derivative is simply a 1 plus 2 a 2 x plus 3 a 3 x square, and these are just n 1 n 2 n 3 are polynomial functions unknown as yet, but we know that they are functions of x. So, there can be derivatives, then their first derivative. So, d n 1 by dx multiplied by v I plus d n 2 by dx plus multiplied by theta I plus d n 3 by dx multiplied by v j plus d n 4 by dx multiplied by theta j. So, this interpretation will have correct limiting behavior if it reproduces the nodal displacements and slopes when evaluated at nodes, and therefore, assuming without any loss of generality that the node I has the let us say coordinate of node I is 0 and coordinate of node j is L. So, then this a particular approximation that we have, this can be again written as 1 x x square x cube multiplied by a 0 a 1 a 2 a 3, and then it can be evaluated. So, that is what it comes here, V I is equal to a 0 plus a 1 x I plus a 2 x I square plus a 3 x I cube. Theta I is given by a 1 plus twice a 2 x I plus thrice a 3 x I square, and similarly for node j. Now, substituting the values for x I and x j, and this is what we get, x I is equal to 0 and x j is equal to L. So, that is straightforward. Now, this coefficient matrix can be inverted, and I can find relationship between a 0, a 1, a 2 and a 3 in terms of v I, theta I, v j, theta j, and when I invert it, this is what I get. You can work out yourself if you wish, and this is what we will end up with, and this we can substitute in the original approximation for the transverse displacement, and we end up with this expression. So, transverse displacement is equal to these polynomial terms multiplied by the coefficient a 0, a 1, a 2, a 3, and if I collect these terms, these are the terms I get. So, this is 1 by 4 and this is 4 by 4. So, product is 1 by 4 again, and these are the 4 interpolation functions that will be multiplied with respective primary variables. So, n 1 v I plus n 2 theta I plus n 3 v j plus n 4 theta j. So, that is the interpolation model for Euler-Bernoulli beam, and this is the cubic Hermite interpolation polynomials. You can, this of course we derived from the first principles, but as an exercise you can possibly go back to our discussion of the interpolation theory and look at the expression for Hermite interpolation, and there is a generic expression that is given there, and you can straight away derive the equations, interpolation functions from that generic expression, right, and you will get the same expression. So, this is the basic finite element approximation. So, how does that lead to our finite element equations, equilibrium equations? So, that is what we will discuss in our next lecture. Thank you.